Hi everybody, welcome to this course on modern optimization. In this first video, we shall introduce what optimization is about. Then we shall quickly move over to this new set of approaches that we term modern optimization. Finally, we shall wrap up by seeing a few examples of the applications of these modern optimization methods. So this will be a gentle start to this exciting series of videos. From the next video onwards, we shall take a deep dive into how to use these methods. So let's begin. So optimization is about making the most of something. Suppose you wish to achieve something in life. Say you want to maximize your happiness, or say you want to minimize the disease prevalence in the world. The words like maximize and minimize indicate that you can try your best, but the results may be limited by the range of possibilities in front of you. So exploring the range of possibilities is the core of optimization, and we shall return to it several times during this course. Next, while you explore these possibilities, we must have an objective in mind. While in life these objectives may be fuzzy or abstract, like happiness, in optimization the objective must be computable. That is, we should be able to check if we are now at a better stage than before or not. Also, if it helps, if it is easy to compute that objective, otherwise the optimization process can become slow, unreliable, or even impossible. Some common applications of optimization are cost cutting and maximizing profit. So a business, for instance, might want to choose from a range of options so that it can produce a product at minimal cost, but with maximum profit. Likewise, if you have a data mining or data analytics background, you'll be familiar with the fact that we are often concerned with minimizing some error function, essentially error in our predictions. So an optimization process works behind the scenes to minimize that error. Still more examples are producing a great design, and we shall see examples of that. We can use optimization to produce a timetable that meets all the strict requirements and maximizes satisfaction on the optional requirements. Still another example is to minimize energy wastage without compromising your comfort in your home, for instance. So hopefully you can appreciate that optimization is common in life and business. However, optimization can be quite challenging for various reasons. And one of the reasons is that often there are far too many options. For instance, see this figure on your screens. The z-axis, the one that's going vertically up, shows the loss of some sales in some business. And we want to minimize the loss by selecting values of the two variables on the x-axis and y-axis. As you can imagine, even for just two variables, there are infinitely many real values. So to explore all these combinations of values is very challenging. Secondly, as you can see, if you move in the xy space, it is not easy to decide which way to go consistently, because sometimes the loss, as plotted along the z-axis, increases and at other times it decreases. So if we view this graph as a landscape, then it is quite a rugged or deceptive landscape, so to speak. You may say, well, we can see the arrow that points to the best solution, or the so-called global minimum. But notice, in practice, you will not have such a picture to see. In fact, you will simply have to try something and then see the result of your trial. And then you have to guess how to tweak your solution so as to move to a better result. So another problem is that while you optimize, you may come across some solutions that are infeasible. For example, a computer can easily propose that to maximize profitability of a business, the workers must work round the clock. But that is not feasible. So an optimization process must work within a feasible space of solutions. Moreover, with optimization, there is no guarantee that you will always get to the best solution possible. We also call the best solution possible the most optimal solution or the globally optimal solution. Furthermore, if the cost of evaluating a solution is too high, then the cost of the optimization process itself will be very high. Therefore, a lot of optimization research is about reducing the cost of evaluating a particular solution. Finally, often we have multiple objectives in mind and we want to optimize them together. But some of these objectives may work opposite to each other. For example, you can maximize your income by increasing hours of your work, but at the same time you reduce your leisure or family time. So while you try to maximize your income, your overall objective is to maximize the quality of life. And that is actually a multi-objective task because quality of life, as we have said, we seem to have alluded before, is actually a combination of various objectives. And you have to balance those multiple objectives out. So that is challenging. Now, if you are into data mining or data analytics, then you also need to understand that optimization is behind the success of such algorithms. Now, if you do not understand these algorithms very well, do not worry. We're not going to go into the details of that, of these algorithms. But I have listed a couple of names on your screens. Both of them uses an optimization algorithm to produce the best results possible. There are a couple more names, but essentially all these algorithms, from neural networks down to decision trees, use an optimization algorithm behind the scenes that minimizes the errors on their predictions. So if you've used these methods and you just run these methods and out pops a result that has minimized some error function, well, remember that there is an optimization process working behind the scenes. Likewise, there's another data mining algorithm called clustering algorithm, and these algorithms are used to classify data into clusters. So these algorithms ensure that the clusters are tight but well separated from other clusters. Therefore, the cluster tightness and cluster separation act as multiple objectives for the optimization methods. So let us formalize some notation now. The objective in optimization is specified with a computable function that is called an objective function, and as the slide title says, that is the end goal in optimization. We are always trying to maximize or minimize a certain objective that is in front of us. So we can specify whether we want to maximize or minimize the objective function. So I'm using some mathematical notation here where I say f is a function, it is the objective function, and to evaluate this function we take as input some variables that we label x1 through to xn, and once we have supplied the values of these variables x1 through xn, the function f is able to compute an objective value. So here the variables x1 to xn are called the design variables because the values of these variables are chosen to design a system or design a solution to our problem. Okay? And the function f then just tests out how good that solution is. For example, If we are maximizing profitability for a shop, then the design variables are the set of prices we want to set, because we want to test, well, in what prices should we set so as to attract the customers and so that our total profit margins just go up. So for example, here I show a bunch of prices. So if we can write an objective function f that can compute the profits, then all these prices will be fed into that function. And that function f will just tell us what profit we can generate for this set of prices. So another convention, another notation to learn, another term to learn, if n, that is the number of design variables, is finite, we call our optimization problem as a finite dimensional problem. Okay, for example, if we have to set the prices for 5 products, then we have a 5-dimensional problem. Sometimes n can even be infinite. So we then have an infinite dimensional problem. Here I shall give you an example that may be quite counterintuitive to many of you, but bear with me. Suppose you want to automatically generate a sequence of instructions that guides a robot on the surface of Mars without failing. Now, how long that sequence should be? Do we know that? Well, if we are very well invested into that problem, maybe we are able to put some limit on it, but in general, it's hard to imagine the length of such sequence. So potentially the sequence can be of any length. Hence, this is an example of an infinite dimensional problem where each instruction represents a design variable. So do not worry if you do not fully understand that, because we shall discuss these things later in detail. But for now, just try to get your head around these concepts as much as you can. Notice this course is about modern optimization. So that means there's a bunch of traditional optimization approaches as well. So we call the traditional approaches as mathematical approaches or mathematical optimization algorithms, as appear to the left of this tree. The mathematical methods are also called numerical methods, and they are taught as part of applied mathematics courses. These methods require certain assumptions, and if those assumptions are fulfilled, they work very well. However, in this course, we shall show that there are situations that these methods do not work, and therefore the so-called modern optimization methods have become popular. Now, popular numerical methods include names such as linear programming, integer programming, nonlinear programming, and there are others. Whereas the modern optimization algorithms are also called probabilistic methods or metaheuristics. They relax many assumptions of the numerical methods, and therefore they can work on problems where numerical methods do not. However, since these methods are probabilistic, there is often a high probability that the methods do not return the best possible result. Therefore, they are most useful in situations where you can relax your expectations somewhat. But the problem itself, the optimization problem itself, is so complex that the traditional methods do not work. Modern optimization methods include names, as on your screens. And if you notice carefully, you'll see that these names draw often from biology and nature. Hence, we see names like evolutionary algorithms, ant colony optimization, particle swarm optimization, and many other names. Now, in this course, we shall specifically target evolutionary algorithms. This is a set of methods that solves computational problems, but this set of methods is designed in terms of natural evolutionary principles. In essence, these methods simulate natural evolution and solve computational problems. They are now well established with big companies, in fact, like Google and Uber. They're using them. Okay, so before we proceed further, I invite you to some reading and some self-exercise. You can do the exercise alone, but it will be best to discuss your attempts with study partners. So read up the link on your screens until the subsection called major subfield. So if you go to this link, which is on the top of the slide, okay, it'll open a page and you start from the top of the page and you can stop reading when the subsection titled major subfields start. Now the link to this link is also given in the description of this video. Alternatively, just Google mathematical optimization Wikipedia or something, so it will pop up straight away. Notice this exercise asks you to familiarize yourself with the notion of objective function and how to write out the objective function. So you'll go through some conventions. Also understand the terms such as maximization or minimization, candidate solutions, local maximum, minimum, and argmin. So there are quite a few notations or conventions for you to familiarize yourself. This exercise will get you ready to understand some basic conventions of optimization literature. So you can pause the video and start reading. And once you finish, you can return to the video from that point onwards. But if you're familiar with this, you can move on. Okay, so now we'll go through some examples of the applications of modern optimization methods or metaheuristics. So the first example is antenna design. In early 21st century, NASA decided to design nanosatellites. The rationale was that making many small satellites will be more cost effective than building one large satellite. Therefore, they had to miniaturize everything inside a satellite. Now, what is the most important component of a satellite? Well, it has to be an antenna. After all, a satellite has to send and receive signals. So NASA utilized a modern optimization method to design their antenna. This automatically produced antenna that is showing on your screens beat the best human designed antenna produced by another NASA team. And it beat it on many factors. For example, this automatically produced antenna took 2/3 less time to manufacture, and it had the best radiation patterns. The meta-heuristic used to produce this is called genetic programming. And the objective function, for those of you who completed the exercise earlier on, is on your screens. Notice the objective function it shows that this is a minimization problem, where genetic programming tried several thousand antenna designs and chose the one that minimized the product of 3 factors that are on your screens. The details of these factors are not important at this stage. What's important is for you to understand that these 3 factors represent some qualities of the antennas that were produced. And the lower the product of these 3 qualities, the better the antenna. Notice also that in this case, the antenna was not designed by physically creating thousands of antennas. Instead, genetic programming was able to create a series of antenna design instructions as on your screens. These instructions were passed on to a software or antenna simulator that simulated an antenna with the given instruction sequence and then produced the 3 values for the 3 quality factors that we mentioned earlier. And these quality factors were then multiplied to compute the objective function. So genetic programming produced thousands of different sequences of such instructions, and chose the best sequence. Hence, the domain of the solution is a sequence of instructions. That is, we draw our solutions by combining different instructions in different sequences. Another well-known application of metaheuristics is the so-called traveling salesperson problem. Here, a salesperson has to visit many cities, and these cities are represented by dots on a map, as on your screens, and the task is to find the shortest route through all these cities. A common metaheuristic for the TSP problem is genetic algorithms. And the objective function here is to find a route that minimizes the total distance covered. So genetic algorithm produces thousands of different routes and finally outputs the one that has the minimum distance. Hence, the solutions are routes or visit sequences in the form of city indices. So a sample solution could be a route that starts with city C3 and then moves on to city C1 and eventually finishes off with cities C30 and C20. So now there are many examples of applying genetic algorithms on the TSP problem, and it's quite common for the new practitioners of genetic algorithms to try genetic algorithms on this problem. So you can Google traveling salesperson with genetic algorithms and you'll find many examples and many implementations. So here is a sample solution for this problem that has been plotted graphically, and you can see that the genetic algorithm was able to produce a route where the salesperson visits each city only once. So because there are no multiple visits, this represents the shortest route. Here's another and the final example in this lecture of the application of metaheuristics. And in here, a metaheuristic algorithm was used to create intelligent game-playing agents for Atari games. Atari games provide some popular toolkits for designing your own game-playing agents. Since an agent is nothing but a set of instructions, game-playing instructions, the appropriate metaheuristic is genetic programming again, because genetic programming involves sequences of instructions. Here the objective was simple, that was to maximize the game score of the playing agent. So again, genetic programming just produced thousands of different agents, or essentially thousands of different game-playing instruction sequences, and picked the best of the lot. If you want to find out the details of this method, check the links on your screen or see it in the description below this video. So with that brief introduction to modern optimization, I conclude this video and will see you in the next one.